Hello everybody, welcome back to my channel where we solve rather difficult integrals. And today's integral is a very interesting one in my opinion. It is not so difficult, but it can be a very good integral to try to use special functions. And I have no tools, so it is an integral I wanted to calculate with you because it is a very good integral to improve our skills in evaluating definite integrals. And well, okay, first of all, what do we think about when we see our integral? It has boundaries. It is a definite integral from 0 to pi by 2, which are very nice boundaries when we have tangent theta. We have trigonometric functions outside of and inside of it our variable, and we don't have any theta outside of a trigonometric function, which means no need to think about iteration by parts. This shouldn't be helpful, but well, we will see. Maybe we will use it, but it is not the first thing we want to think about. What else? We have tangent theta, and we know the substitution. If we know that if we let x being tangent theta, we have d theta, which is being equal to dx by 1 plus x squared. So we can make polynomials appear instead of the tangent theta. We would have outside of the logarithm, we would have 1 by 1 plus x squared, and then logarithms. So logarithms and polynomials, well, inverse polynomials. What do we think about? This might be helpful if we want to do a series expansion. And well, the boundaries are from 0 to are 0 and pi by 2, and with this substitution it becomes 0 to positive infinity, which are very common boundaries with special functions. So we must think about special functions that may be helpful here. Then we see that we have theta inside of a trigonometric function, and then inside of a logarithm function, which is usually pretty much impossible to solve just right now. Maybe we have an antiderivative, but clearly, well, not here. We cannot integrate just right now logarithm squared of tangent theta, or at least not without a substitution. So letting logarithm tangent theta remain itself won't be very helpful. We must do a substitution that will simplify our integrand. So, well, we don't see very many substitutions here. Well, maybe we could try logarithm tangent theta being our new variable, but in my opinion, first, a good idea may be to try to get our new variable being not so different of the first variable. If we let logarithm tangent theta being the new variable, the d theta will be very, very difficult to explain, and we will have a probably very difficult integrand in the end also. But if we try just x being tangent theta, we will always be able to then, here this will be the new variable, let's say x, we will be able still to let logarithm x being a new variable, let's say u. So first of all, when we try substitutions, do the easiest substitution you can, and don't try to just take the whole function and letting this be the variable. It is not very useful all the time. So first of all, we just do tangent theta equals x. Tangent theta equals x. We do the reciprocal. We have theta being arctangent of x. The substitution is valid because we have from 0 to pi by 2, so tangent is continuous. It looks this way, 0 pi halves. And you see that is a, well, we don't have any problem like if we had this kind of boundary, 0 to pi, so no problem here. and then we differentiate theta and our tangent x, and we have the theta being dx by 1 plus x squared. Alright, 0, we need to calculate the new boundaries. 0 is the value of theta at the beginning of the interval. So we need now the value of x. Tangent 0 equals x, so x is 0 when theta equals 0, so 0 goes to 0, and then pi by 2 goes to what? Pi by 2 is the value of theta. Tangent theta is positive infinity, so x equals positive infinity, or goes to positive infinity, as you want. A question we might ask ourselves is, well, as you see, tangent theta in pi by 2 equals positive infinity, but also negative infinity. So which one do we need to take? Well, it is very easy. You see that our interval is our interval is from 0 to pi by 2, so you need to consider the sign of the variable, here x, on this interval, and you see that x is equals tangent theta, but is always positive. You see that tangent theta goes to positive infinity. It only equals negative infinity after pi by 2. Here, tangent theta equals negative infinity, but here it is positive infinity. So the value for x is not negative infinity, it must be positive infinity. And well, even worse here, if we tried negative infinity, we would have logarithm of a negative value, so it would be invalid. So we must take positive infinity. I equals the interval from 0 to infinity of logarithm squared x dx by 1 plus x squared. Okay, now we have an interval from 0 to infinity of logarithm squared by 1 plus x squared dx, and it is maybe a easier interval than what we have in the beginning. So, well, we want to progress. What can we do? We can think about series expansion, because here we have an interval from 0 to infinity, but, well, when we have polynomials and even better logarithms, we always need to think about the substitution x equals 1 by u, which can reverse the boundaries. So very nice when you can reverse the boundaries without really changing them. And when we have inverse of polynomials, this substitution may save you even better if you have a polynomial of the second degree here. And if we tried this, well, we can prove that this interval is exactly twice the interval from 0 to 1 of the same function, the x, logarithm squared of 1 plus x squared. So if we wanted to do series expansion, the fact that we need here x being smaller than 1 in absolute value is really not a problem, because we can change our boundary from positive infinity to 1. So the golden question here is series expansion really an option? Will series expansion help us to calculate our interval? In fact, no, but it was a very valid question, because here we have logarithms and we have 1 plus x squared, so probably we would be able to do the substitution, and it would be very easy to totally get rid of the interval and only be left with a series. But in fact, the series would be near to impossible to evaluate, because it is a very, very difficult series. Well, still we can calculate it, but, well, very, very difficult. So do not even try, it is just a waste of time. So this was an option, but, well, we see that it won't help us here. So we have to think about something else. What do we see then if series expansion do not work? We can try to look at the boundaries. From 0 to infinity is a very, very, very common interval of integration for special functions, like, I don't know, the beta function, the gamma function. The zeta function, pretty much any function, any special function defined as a definite integral, if it is not 0 to 1, it will be 0 to infinity in most of the time. So we have to think about special functions here. And what do we have? We have logarithm, and we have 1 by 1 plus x squared. Maybe, usually with special functions, we have some x to an exponent. So logarithm of x may be seen as the derivative of some special function in some way. So, well, what we can do is just try to use Leibniz rule here and creating a function like, I don't know, I lack of imagination, so let's say I of s being the integral from 0 to infinity of x to the s power dx by 1 plus x squared. And you see that if we differentiate our function I, we will get, after differentiating twice, we will get logarithm of x and then logarithm squared of x. And this can be linked to our function I. Our integral I. So this function, if we are able to calculate it, may just give us the result right now, because we can just differentiate it and calculate a special value. And in fact, this is the easiest way to solve it, in my opinion. So, well, we will just try this, but first, in this kind of integral that can be linked to the gamma function, to the beta function, to this kind of functions, we really like to have here the exponent not being x to the s power, but x to the s minus 1 power, because then we have dx by x, and well, it will be easier, you will see. So it is absolutely not an obligation to do s minus 1 instead of x. It would be exactly the same function, but just the interval is changed, so we don't need the same value. But, well, this is just easier to handle if we have x to the s minus 1 when we do these substitutions. It is totally irrelevant. What do we see now? We have an interval from 0 to infinity. We don't have any exponential, so this is not the gamma function. This is not the zeta function, but, well, okay. Maybe we can think about a function that is only defined by here polynomials and divided by another polynomial. So okay, it may be unclear, but I will try to define the special function beta. Beta is defined for two arguments, let's say a and b, as the integral. Well, it has many definitions, but the one we look here is the only one that is for an integral from 0 to positive infinity. So integral from 0 to positive infinity of x to the a minus 1 power dx divided by 1 plus x to the a plus b power. This special function may be linked to our function I of s. So our goal is to transform this integrand in order to get the same integrand here, and then we would have the value of a, the value of b, which will depend on the value of s, obviously. So here we need to do a substitution. What is our substitution? Well, we don't have anything to do except trying to get rid of 1 plus x squared. We don't like the squared here because you see that the power for the beta function is 1 plus x, the whole thing to the a plus b power, and not just x, so we must here get rid of the exponent. So, well, let's say t being equal to x to the second power. Well, dt equals 2x dx, and if I divide by x squared, we have here dt by t is nothing but 2 dx by x. And here you see that we have x to the s minus 1 power, which can be seen as x to the s power times dx by x. So in fact, this here power minus 1 and, well, power negative 1 and then the x is nothing but the x by x, which is dt by t, the whole thing divided by 2. So now we have a easier function, I of s. We have the integral, obviously the boundaries remain the same. So from 0 to infinity, x to the s is nothing but x squared to the s by 2, which is t to the s by 2. So we have t to the s by 2 power. We have here dx by x, which is 1/2 of dt by t. So dt by t, and we don't forget the 1/2 as a factor of the integral. And we have 1 by 1 plus x squared, which is 1 plus t. Okay, now this is a huge progress, because this can totally be linked to the beta function. You see that here we have 1 plus x, and here 1 plus t, so, well, as t and x are dummy variables, it doesn't change anything. You have here x to the a minus 1 power dx, and here t to the s by 2 minus 1 power dt, because here we again have 1 by t, which is exactly t to the negative 1. So here we already have our beta function. We see that here a minus 1 equals s by 2 minus 1, because this divided by t is like an exponent, negative 1. And we have here the exponents 1a plus b, which is not seen, which means this is to the first power, so a plus b is nothing but 1. Well, this is a very easy system. So a equals s by 2 and b equals 1 minus s by 2, which means I of s is nothing but 1/2 of beta s by 2 1 minus s by 2. This is a symmetrical function, so you can define here x to the b minus 1 power instead of a minus 1, doesn't change anything pretty much. So okay, this is our function I of s, and, well, we know that it is a very important identity. Beta of ab equals gamma of a times gamma of b divided by gamma of a plus b. So here we have gamma of s halves times gamma of 1 minus s halves, and the whole thing divided by gamma 1. So here gamma 1 is nothing but 1, because a plus b is defined as 1. And we have gamma 1 minus, gamma s halves times gamma 1 minus s halves. So I of s is gamma s halves, gamma 1 minus s halves, whole divided by 2. And we know that gamma of anything times gamma of 1 minus anything is pi times cosecant anything, so, well, cosecant pi times anything, so we have pi cosecant pi s by 2. I won't prove it right now, but it is a very important relation again. So our function I of s is nothing but pi halves times cosecant pi s by 2. So okay, we have our function I of s, and we need the particular case. Here the derivative of our function I, the second derivative, and then we need the power here s that makes s to the anything power disappear, which means s minus 1 equals 0, because x to the 0 power is 1, which means s equal 1. From this definition, you see that I dot of s is the integral from 0 to infinity of logarithm squared x to the s minus 1 power dx, all divided by 1 plus x squared. So you need here s minus 1 to be equal to 0, so our integral I is the case I dot dot of 1. So first we calculate the second derivative of our function I. Alright. I dot dot of s is d squared by ds squared of pi halves cosecant pi s by 2. So the pi half here is a constant, so we can just bring it outside of the derivative. And cosecant pi s by 2, we have to differentiate the cosecant, but we also must think about the chain rule. We have the pi by 2 as a factor of the argument, as a factor of the variable inside of the cosecant, so as the argument. So the chain rule says that we have here pi by 2 from the pi by 2 here that we just bring outside, and then we have the factor of s, pi by 2, to the second power times the derivative of cosecant. And I mean the second derivative of, then we can say cosecant dot dot of pi s by 2. The derivative of cosecant, well, we know it. We know that cosecant is 1 by sine, so when we do the derivative, it is, okay, we have 1 by u, so we have negative u dot by u squared. U dot is sine dot, which is cosecant, so we have negative, no, not cosecant, cosine, I mean, so we have negative cosine divided by sine squared, and then we differentiate again. Now we do the u by v. Here this is u, this is v. U has the negative cosine. So we have u dot first times v. So u dot is sine because cosine has the derivative being negative sine. So we have an extra negative sign. So we have sine, which is the derivative of u, times v, which is sine squared. And then we have negative u times v squared, which is, so negative cosine, it is a positive cosine times the derivative of v, which is 2 cosine sine. And the whole thing is divided by v squared, which is sine to the 4th power. So, okay, here we have 4 power, which can be bring to 3. We have here sine and sine, which cancel out because we have sine everywhere. So we have sine squared plus 2 cosine cosine, so plus 2 cosine squared, divided by sine to the 3rd power. So I dot dot of s is nothing but, here we have pi to the 3rd power divided by 8 times cosecant dot dot of pi s by 2, which is, here we just take the value pi s by 2, so we have sine squared pi s by 2 plus 2 cosine squared pi s by 2 divided by sine cubed pi s by 2, and we need the value s equals 1. So I equals pi cubed to the divided by 8 times here, okay, we have s equals 1, so we have here pi halves, pi halves, pi halves. We can just get rid of the s. Sine squared of pi halves equals 1. Cosine squared of pi halves equals 0. And sine cubed of pi halves equals 1. So we're left with pi cubed by 8. Which means that the integral from 0 to pi by 2 of logarithm squared tangent theta d theta equals pi cubed by 8, which is a very interesting result in my opinion. As you saw, this was not very a difficult integral, or at least not as difficult as what we've seen previously. So I hope you enjoyed the video. I hope you understood all the calculations I've made here. And if not, then check out my next video so that we can improve our skills in calculating integrals. See you next time, and until then, study, learn, and progress.